Hey there everyone. Today we're going to be learning about the sum and difference identities. These identities are used when you're trying to find the exact value of a trig expression that's not on your unit circle. For instance, if we're trying to find the sine of 15 degrees, we can't just look on our unit circle to get the exact ratio. We could put it in our calculator and get an approximate value, but for this problem they want us to find the exact one. And so we're going to have to use what's called the sum or the difference identity. So the way that you use these is you have to think of the angles that you do have on your unit circle. The ones that we do have would be 30 degrees, 45 degrees, 60 degrees, and any multiple of these numbers. So if we can imagine two of these numbers that when we add them or subtract them give us 15 degrees, we're going to want to use those in these identities. So the first two that I listed come to mind pretty quickly because I know that 45 degrees minus 30 degrees is 15. So the first thing you want to do is rewrite that this is the sine of the difference between those two angles, 45 degrees minus 30 degrees. And again, we picked these two because we know they're both on our unit circle, and when we subtract them, they'll give us 15 degrees. So now using the identity, I have to look and see, okay, is this a sum? Nope, I'm subtracting. So I'm going to use my difference identity, and we're using sine, so I'm going to use this difference identity right here, sine of alpha minus beta is equal to sine of alpha times cosine beta minus cosine alpha sine beta. So all we do is we replace in our identity alpha with 45 and beta with 30. So I'm going to say this is equal to sine of 45 degrees times the cosine of 30 minus the cosine of 45 degrees times the sine of 30. Okay, just be real careful about what you're plugging into where. Alpha was our first term, beta was our second. So all the alphas become 45s and all the betas become 30. Now, because these are on our unit circle, I can actually evaluate each of these individually. So the sine of 45 degrees on my unit circle is square root of 2 over 2. And the cosine of 30 degrees is square root of 3 over 2. Cosine of 45 degrees is square root of 2 over 2. And the sine of 30 degrees is 1/2. So after evaluating all those, we can see that if we just multiply straight across, we can simplify this fraction. Square root of 2 times the square root of 3 is square root of 6. Make sure you multiply these before you start subtracting. Follow order of operations. And 2 times 2 is 4. And then we're subtracting square root of 2 times 1, which is square root of 2. And 2 times 2 is 4. And since we have two fractions, as long as we have the same denominators, we can subtract the numerator. We're just going to leave it as square root of 6 minus the square root of 2. We can't actually subtract them, so we'll leave them as a binomial expression. And then the common denominator here is 4, so that I can just write that as one big fraction. And that is your exact value for sine of 15 degrees. Okay, works the same way with radians. You have to think a little bit more creatively about how to split it up though. For instance, when I have 7 pi over 12, I want to think of numbers that I can add to equal 7 that would be reducible when I put them over 12. For instance, I can think of 3 pi over 4, that's on my unit circle, plus, 3 pi over 12, that's reducible, plus 4 pi over 12. 3 pi plus 4 pi is 7 pi, and I can reduce both of these, right? 3 pi over 12 reduces to pi over 4, and 4 pi over 12 reduces to pi over 3, both of which are on my unit circle. So I'm going to change this to the tangent of their sum. Okay. Now, if you have trouble with this, can you convert from radians to degrees? Absolutely, and then just do it the same way we did A. But the purpose for this practice problem is for you to get practice using them in radians, which can be slightly faster if you can think of them. So the tangent of pi over 4 plus the tangent of pi over 4 plus pi over 3, we're going to use our sum identity right up here with tangent. Tangent of alpha plus beta equals this fraction, tangent of alpha plus tangent of beta, all over 1 minus tangent alpha tangent beta. So this is pretty much a plug and chug. I'm going to replace tangent of alpha with tangent of pi over 4, plus tangent of beta, which is tangent of pi over 3. Divided by 1 minus tangent of pi over 4 times the tangent of pi over 3. And when we go to the unit circle, tangent of pi over 4 is 1, plus the tangent of pi over 3 is square root of 3. And again, the tangent of pi over 4 is 1 down here, so this is just 1 times the tangent of pi over 3, which is again square root of 3. Okay, this is our answer. If we want to rationalize it, we can multiply it by its conjugate. The conjugate of the denominator down here would be times 1 plus the square root of 3. If we do that to the top and bottom, it makes it somewhat simpler. This is equal to 1 plus the square root of 3 times 1 plus the square root of 3. And the bottom, when we multiply the conjugates, we get 1 minus 3. So when we distribute, this is 1 plus 2 square roots of 3 plus 3 over 2, negative 2. And lastly, we get 4 plus 2 square roots of 3 over negative 2, which can reduce to negative 2 minus the square root of 3. Okay. Try these two on your own. I'll put up the answer in a second. Okay, here's the solutions. You should have broken down 45 minus 30 to be 15 degrees, and then used your difference identity with cosine, which is cosine of alpha times cosine of beta plus sine of alpha times sine of beta. And you'll notice that a lot of these solutions are very similar, but there are some key differences. Compared to our first example, this was root 6 plus root 2 all divided by 4. And if you looked ahead at 1b, when you solve that one, you get the exact same thing, square root of 2 plus square root of 6 all over 4. There is an identity that lets us know 5 pi over 12 is the same thing as 75 degrees, which we notice is complementary to 15 degrees. So the cosine of 15 degrees should be equal to the sine of 75. That's our cofunction identity right there. And this is kind of proving it. Okay. Here are some practice problems for you to attempt. We will work more on these in class. And that's it for now.